quantum gravity is important for understanding certain processes in the universe, in particular in very extreme conditions. So, for example, what happens in the interior of black holes where the universe inside the black hole collapses, or what happens at the very beginning of the Big Bang, perhaps even before inflation, when you had this initial cosmological singularity or some region. Singularity means that we don't understand it using the Einstein theory of gravity. So we need this. We think that if we had the quantum version of the theory, then it would be non-singular. It would be something that we could understand. So, in fact, this problem of the beginning of the Big Bang is the most interesting problem that quantum gravity could address.
Hello, this is Robinson Erhardt here with the introduction to Robinson's podcast number 177. And this episode is with Juan Maldacena, who is one of the biggest, figuratively the biggest and most influential figures in theoretical physics today. And he's also the Carl P. Feinberg Professor in the School of Natural Sciences at the Institute for Advanced Study. So Juan is mainly focused on quantum gravity and string theory in particular, which is the majority of what we discuss in this episode. The first quarter, I'd say, is a warm-up. And it's a warm-up for a lengthy discussion of his paper, The Large N Limit of Superconformal Field Theories and Supergravity. And it has about 24,000 citations, which is, I believe, or which makes it, though I could be wrong, the most cited paper in high energy physics of all time. And the rough gist of this paper, which is an example of the holographic principle, is that a theory of quantum gravity in an anti-de Sitter space has a parallel description, or it can be translated into a conformal field theory that describes the physics in a space of one less dimension on the boundary of that bulk space. And then maybe to put that a bit more simply, I hope, and extrapolating from the conjecture to our universe, so assuming that it holds here, that it holds there too, even since it's a conjecture, and that our universe is or does admit of a string theoretic description, then the theory that describes everything in the bulk of our universe, so you, me, the Milky Way, and so on, would be translatable into a conformal field theory that describes processes occurring on the boundary of our universe. And then maybe translating it again into another example, though it's no longer the same AdS CFT correspondence, but some results regarding black holes that I discussed with Eric Verlinde in episode 159. Everything happening on the inside of a black hole can be read off of its boundary. And of course, we get into a lot more depth than this and hopefully break it down into much more easily digestible parts and motivate why this is so interesting, and also clear up any mistakes that I may have just made. But it's a terrific episode. Juan, it goes without saying, is amazing. And now, without any further ado, I hope you enjoy this conversation as much as I enjoyed having it with Juan. We don't need to get into this right now, but because string or M theory, it remains controversial among physicists. I always find it fascinating to hear why some physicists gravitate toward it when others don't. And over the past couple of decades, you've been one of the central figures in the area. So I can't help but ask just what sorts of considerations, whether they're philosophical, mathematical, physical, or otherwise, led you to gravitate toward it already when you were in graduate school?
Well, I should say that before we talk about string theory, let's try to explain the problem that it tries to solve. So it's the problem is to understand the quantum mechanics of space-time. So Einstein theory of gravity consists of the idea that space-time is curved and dynamical. It can change and so on. But it's a classical theory. So in the sense of classical mechanics, it's a classical, let's say, field theory. On the other hand, we know that matter at short distances is described by quantum mechanics, a new type of law. And other classical field theories, such as electromagnetism, that describes the electromagnetic field, are really fundamental. They're changed by quantum mechanics and are, and that's important. I mean, we describe interactions of matter with light using this quantum theory. So the question is gravity also quantized in a similar way? And what are the formulas that describe this new quantum theory? Now, let me say why we care about this problem, why we care about the quantum theory of gravity. Now, for most practical purposes, we don't care. So if you are interested in building a better iPhone, or you are interested in some very practical technology, it's going to be totally useless. And the reason is that gravitational coupling is very small, and that this makes these quantum effects very small. However, quantum gravity is important for understanding certain processes in the universe, in particular in very extreme conditions. So, for example, what happens in the interior of black holes where the universe inside the black hole collapses, or what happens at the very beginning of the Big Bang, perhaps even before inflation, when you had this initial cosmological singularity or some region. Singularity means that we don't understand it using the Einstein theory of gravity. So we need this. We think that if we had the quantum version of the theory, then it would be non-singular. It would be something that we could understand. So, in fact, this problem of the beginning of the Big Bang is the most interesting problem that quantum gravity could address. Other problems, as I said, were problems involving black holes. So that's the context. That's why we want a theory of quantum gravity. Now, theories like electromagnetism have been quantized, or the quantum theory was developed using a certain type of technique. And the same type of techniques do not quite work for gravity. And so that's some background. So I gave you why we care about this theory, and second, why the simplest approach doesn't work. I mean, the simplest approach works for some things. So in some approximation, it does work, and it predicts some interesting things. For example, that if you have the theory of inflation, which says that you have some very rapid expansion at the beginning of the universe, then quantum effects should produce gravity waves. So if people are trying to look for them mainly through
I'm talking to Brian Keating tomorrow about this, actually.
Wonderful. Yeah. So it's something that could be detected at any time. I mean, there was a claim of detection a few years ago. Unfortunately, it was incorrect, but by BICEP. And that kind of shows you that they could be detected at any time. And if they are detected, then it would be a real smoking gun of quantum gravity, that gravitational fields should be quantized. I mean, we are assuming the theory of inflation, but and for that, you don't need a string theory or any fancy theory. So it's just the simplest quantization is fine. So the place where you need it is when you try to get something a little more precise or in more extreme conditions. So inflation happens, the expansion of the universe is rapid, but it's not that rapid compared to what we call the Planck scale, which is the scale at which quantum gravity effects are very important. So if we want to somehow go earlier than inflation, then we would need the theory of quantum gravity, and we would need some better theory. Now, string theory is a theory that had a long history, and it originated originally as a theory of the strong interactions, and it was originally based on the idea that instead of particles, we'd consider strings. That's where the name comes from. And this theory was developed, and over the years, then people realized, Yonea and Schwartz realized that it could be used to describe gravity, quantum gravity. And when you use it for that purpose, it leads to well-defined formulas, and it doesn't have the problems that the standard techniques that were used to construct gravity. So you don't have those problems. So at the very least, I think you should think of string theory as a kind of toy model for quantum gravity. So it's a particular version of quantum gravity that seems to be well-defined, where you could compute corrections to any order and defines a kind of what we call a perturbation theory, similar to how we define, let's say, quantum electrodynamics, so the theory that describes the interactions of quantum light with quantum matter. But it's a little more complicated, and it has some various features, and it put some constraints on the solution. So the simplest flat space-time needs to have a specific number of dimensions, let's say 10 dimensions. So it's a very constrained structure, let's say, fairly constrained, and the fact that it's well-defined then allows you to somehow study within this theory various questions relevant to quantum gravity. In particular, it was useful for understanding aspects of black holes. Now you might ask, well, so let me say what string theory has done and what it hasn't done. So it has provided some nice explanation for quantum aspects of black holes. I'll get more into that later. And something that it has not done yet is to understand the beginning of the Big Bang, for example, what cosmology would look like in string theory. So it's a complicated theory. We don't understand it completely. We understand some aspects of it. And at the very least, it's a toy model. There might be other theories of quantum gravity that are that exist, make mathematical sense, but the theory that makes most mathematical sense so far is string theory. So no other theory on the market sort of comes close to it. But yeah, there might be other theories, and maybe we might discover them. And one of the things that has happened is that there were historically other approaches to quantum gravity that people had. For example, 11-dimensional supergravity. And this was thought to be different from string theory and unrelated, and some people said was wrong or so on. But then now we understand that it's kind of part of the same structure, that there is some theory that reduces to 11-dimensional super. So historically it has happened that things that were not considered string theory are now considered string theory. So I think maybe so we've expanded these horizons, and maybe we'll expand them more in the future as we understand that other ideas perhaps are, we find the right place for other ideas as limits of various kinds. So mostly people who are called, let's say, string theorists are people who are interested in this problem of the quantum mechanics of gravity. So gravity and quantum mechanics, space-time and quantum mechanics. And so that's roughly what it is. What it is both from the intellectual point of view and also from the sociological point of view. So someone who works on string theory, let's say like myself, for example, I don't all the time work on the traditional string theory of the 80s. We might work on different toy models that are interesting for quantum gravity. And for example, in the past few years, we've been thinking about something called some model that was inspired by some problems in condensed matter physics. And as far as we know, it's not directly connected to the string theory, but it has some features in common, and has been very useful. So,
Well, that was a terrific introduction. And just though to recapitulate, so I should understand that your interest in string theory stems from maybe two basic considerations. One's a conviction that quantizing gravity, particularly for understanding the Big Bang, is the most important goal of theoretical physics right now. And then second, that string theory is a particularly useful way of doing this, especially, as you mentioned, for studying black holes, though it hasn't quite gotten to the Big Bang yet. And at this point, it's the best for these things mathematically, though, as you mentioned, other theories might arise.
Yeah, I wouldn't say it's the most important goal in in physics. Physics is very broad. It has many interesting goals. There are many interesting problems in physics. This is just one question in physics that is interesting. I find it interesting, but I mean, there are of course many other interesting questions. Another point that I didn't emphasize, but let's say was emphasized a lot in the 80s and 90s, is that we, from string theory, from the 10-dimensional theory, if we put it on some special 6-dimensional manifolds, we could get physics similar to that in our own real world. So it has the ability perhaps to incorporate the rest of physics, the standard model in particular. And there are many ways of doing this. So you can get the standard model, or you could get many other possibilities, and that might be another avenue through which you can connect string theory to reality. So far we haven't connected it, because mainly the main problem was in the beginning people thought that there would be a small number of possibilities, and one of them would be the standard model. But now they realize that there are many possibilities. The number is so big that we could perhaps get the standard model, but we don't have a concrete prediction.
Well, before we get to the connections between string theory and the standard model, one thing that I really feel that I need to ask you about is the Institute for Advanced Study, because you're actually the first person I've spoken to on the show who's at the IAS out of about 200 episodes. And I'm sure that many of our listeners might not actually be familiar with it. But you did your PhD at Princeton, and then you were a professor at Harvard, both of which are tremendous places to do physics. So what was it about the IAS that made it so alluring as your ultimate home for physics?
Well, the IAS is a small research institute focused mainly on research. There are students that do PhDs, and there are students that come from Princeton University. We have a wonderful group of postdocs doing research. So, yeah, it's a great research environment, and there are also other people working in similar fields. Nati Cyber, Edward Witt, and Nimar Kani-Hamed. So it's a wonderful environment, and that's what made me come here. Of course, Harvard is also wonderful, and there are many other wonderful places.
Mm-hmm. Well, I spoke a bit about this with your colleague in the Netherlands, Erik Verlinde, and also Andy Strominger. But toward exploring the AdS CFT correspondence, which is what I hope to get to in this conversation, and which I understand is among the most important results in string theory, I'd like to begin by talking about holography, or the holographic principle. And I know that this was its historical origin, but I think you agree that maybe discussing black holes and Bekenstein-Hawking radiation is maybe the best way to introduce the concept?
Right. So in the 70s, Bekenstein proposed that black holes have some entropy. And then Hawking discovered that black holes have a temperature. So, and they realized, and together with other researchers, they realized that black holes seem to obey the laws of thermodynamics. So it's a bit mysterious that this object that started out as some geometry of space-time, unique geometry, now behaves like a thermal object. And then there was a question that was raised, which was, where are the microstates of the black hole? So what do these formulas mean? So what the formulas mean, taken at sort of face value, is that the black hole can be viewed from the outside as a quantum system. So it's some system that has a finite entropy, so finite number of states. And you can make the hypothesis that it evolves according to some ordinary quantum mechanical laws, though they are not. Though these properties are not manifest from the gravity picture. From the gravity picture, all you can calculate is the entropy. So there was the idea that a better understanding of gravity would lead to an understanding of what the black hole, what these degrees of freedom of a black hole are, or a full description of a black hole. Now, this picture that I just told you is something that you might naively get from these formulas of thermodynamics, but it was not obvious, and in particular, people like Stephen Hawking disagree with this picture. So they were proposing that black holes actually destroy information, so they don't behave like an ordinary quantum mechanical object, but they fundamentally lose the information, at least from the point of view of an observer who stays outside the black hole. This is sometimes called the information problem. And so then, since string theory is a theory of quantum gravity, you can try to analyze this problem in string theory. The main technical breakthrough that made this possible was a discovery by Joe Polchinski of something called D-branes. I will not get into the details of what they are, but they are some other objects that string theory has. So string theory has these strings, but then it has these other objects. And they have two very important properties. One is that they're on the verge of becoming black holes. So they are, if you just take one or two of them, they behave like a very fundamental object, which is a very precise description. But if you take many of them, they start curving space and they start to behave more and more like black holes. So that's one point. And the second point is that, Polchinski gave a very precise description of the excitations of these objects, so how they interact among each other and with the fields outside. And so there are precise mathematical formulas that tell us how this happens. So roughly speaking, what happens is that on these objects, the excitations are described by certain theories that are similar to the theories that describe elementary particles, or in particular the strong interactions. But what's important for this is that they follow well-defined quantum mechanical rules. And so with these D-branes, you could define quite easily as so-called extremal black holes. So the simplest low energy system. If you take these D-branes at low energies, they have many properties in common, and you can view them in some limits as black holes. So extremal black holes are black holes that carry some charge. And so such black holes have a mass which is bigger than the charge. And as you lower the mass, the Hawking temperature becomes smaller and smaller. And when the mass is equal to the charge, they become a very cold object. So, but with still large entropy. And this large entropy was first derived and reproduced by Strominger and Baffa using precisely these rules of D-branes. And then after that, a bunch of us started trying to understand what happens when the temperature is not exactly zero, so it's a little bit above zero. So there, you can have some more non-trivial dynamics. You can throw things into the black hole can evaporate, and so on. The idea is that what happens with these black holes is that they have a geometry which is flat space very far away. And then as you approach the black hole, they develop a long kind of throat or region where the gravitational potential becomes smaller and smaller. If you look at from the outside, those excitations look like they have lower and lower energy. And so it's a bit like a big gravitational well. And at the bottom of the well, you have the horizon, the black hole. So this AdS CFT correspondence came by saying that this region of the well itself, plus the horizon and so on, can be described by these theories that describe D-branes at low energies that were standard quantum field theories or theories of interacting particles. The geometry of these throats is something called anti-de Sitter space. So it's a negatively curved space. that is very symmetric. It's one of the simplest negatively curved spaces you could have. So that's where sometimes it's called AdS. The anti came from the fact that the actual space that the sitter was a person who considered an expanding universe, and that's called the sitter space. It has positive cosmological constant. It has negative cosmological constant. That's where the word anti comes from. It's trying to explain the name of the space. But anyway, so it's some simple negatively curved space. And so the idea is that the physics in this space is the same as the theory of interacting quantum particles without gravity. So it translates a problem with gravity to a problem without gravity. In particular, in the problem with gravity, you could have a black hole. And then you can describe that black hole from this theory without gravity, and the black hole becomes just an ordinary thermal state, thermal system in this theory. So this allows you, in principle, so it's a conjecture that these two things are equal. It's a conjecture that passes many tests, and there's a lot of evidence for the conjecture. But if you assume this conjecture, then you would have a complete description of these black holes. So the cases that are best understood are cases with lots of symmetries that come from string theory, so in higher dimensions, and very, very idealized cases.
Mm-hmm. Well, that was a great overview, and I'd really like to get into many of the things you just described in more detail. And I'd like to start with the first question that you raised, which is, where are the microstates in a black hole? And one thing that I want to better understand with regard to black holes is, just because the information they contain can be read off as a sort of description from the event horizon, does this mean that the event horizon is all there really is? Because that's the sense I've gotten from some sources that I've read. And if I'm not mistaken, if my memory is not mistaken, Eric Verlin told me that he doesn't really even think about the singularity at the core of a black hole at all, which is where at least we uninitiated into string theory conceive of the information within a black hole residing.
Mm-hmm. Okay, so I think people sometimes say that the information is at the horizon because the entropy is proportional to the area of the horizon. But we don't have any very concrete mathematical theory where that is actually realized. So in AdS CFT, what happens is that you have a black hole with its horizon, and it's within some bigger space. So there's some space that continues. And what AdS CFT tells you is it replaces the black hole and the whole space all the way to very large distance by an alternative theory where that lives basically on the boundary in a sphere very far away, that contains interacting particles, and the black hole is some thermal state in that theory. So that's what we know with precise mathematical description. In that description, you cannot say that the degrees of freedom were at the horizon. In fact, you would also say they are at infinity. They are very far away. So in that sense, the description is very non-local, sometimes also called holographic. Well, it's holographic, where you're looking at it from very far away and you're describing this, three-dimensional space in terms of a theory that lives in the two-dimensional sphere far away. But maybe there is, in the future, people will understand the description where the horizon, you can localize the black hole degrees of freedom at the horizon, but we don't have it yet. So that's one point. The second point is that when we talk about these degrees of freedom, they are the degrees of freedom that describe the black hole as seen from the outside. Right? Now, you might be an observer that's falling into the black hole, right? So if you are falling into the black hole, general relativity predicts that you cross the horizon, you don't feel anything special at the horizon, and that you will then eventually get into the singularity. And maybe you'll die at the singularity. And we don't know exactly. So when we get to the singularity, the current techniques we have, including the ones from string theory, don't tell us exactly what will happen. And so that's something that is currently not understood. That's another question we don't understand in string theory. So through this string theory model, through holography, AdS, CFT, we can describe very nicely black holes as seen from the outside, but we haven't succeeded yet in understanding the black hole interior. There are various ideas people are pursuing, and hopefully will be understood. I think it's very important to understand the interior, because the interior is a region that looks a bit like a mini. It looks like a big crunch. So it's a region. The space-time inside the black hole sort of collapses into singularity, and so if we understood well the interior and this singularity in the future, we could perhaps time reverse that and understand the singularity in the beginning of the Big Bang. So the
right.
questions are related somehow. Yeah, go ahead.
Yeah, one thing that I didn't really understand about Eric's views was that my understanding was the singularity at the center of the black hole is so important because that is precisely where the two theories, general relativity and quantum field theory, break down, because space in general relativity is smooth, but it becomes jittery and chaotic at that level.
Yes, no, that's correct, and I think we don't have an answer to this question. So string theory gives us answers to some questions, but we haven't understood this particular question. So you should view it as a theory under construction. There are many questions that we don't know how to understand, how to solve.
And this is just a terminological curiosity, but do you prefer not to use the word hologram or holography or the holographic principle?
No, yeah, we can use it. So this idea comes basically back to the Bekenstein formula, which says that the entropy of a black hole is proportional to the area rather than to the volume. And then this led to the idea that if you have a region of space, the maximal entropy you can fit in should be proportional to the area, not to the volume. Because otherwise, when we collapse it if we imagine collapsing into a black hole, we would not obey the second law of thermodynamics. And so this led to the idea, to Toft and Susskind, of thinking that you should have this kind of dimensional reduction in gravity, that you have a three-dimensional theory, three space dimensions, but if you take a sphere far away, you should be able to describe it in terms of, or any sphere, you should be able to describe it in terms of a theory that has a number of degrees of freedom, which is at most the area of the sphere. So that's the idea of holography. The AdS CFT correspondence is a realization of this idea when you put that sphere very, very far away. People have made attempts of bringing the sphere not far away, but at more finite locations. And there are some ideas in that direction, but we don't have a precise mathematical description of that situation where you bring the sphere finite location.
The reason that I asked about the term hologram or holography is, and I couldn't tell if you preferred not to use it, and I thought that maybe this would be because it connotes, at least with some physicists and lay people, that the bulk of the universe or the black hole is, in a sense, illusory, and what really exists is this bounding surface, and maybe that was something that you resisted.
No, I think that the two descriptions should be viewed as equivalent, or
okay.
Sometimes it's called the duality, that the two are alternative descriptions, I think. Now, presently we understand better, so in this situation of AdS CFT, we presently understand better the boundary theory. So this theory far away, we think it's completely well-defined. We could do arbitrary computations, at least in principle. But the bulk theory, we don't understand it as well. as well as we understand the boundary theory. And so some people want to say that, or people often say that the space-time in the bulk is emergent. It's some kind of by emergent I mean it's a property that would be true when you have a boundary theory with many degrees of freedom, but not when you have a small number of degrees of freedom. So similar to how, let's say, certain properties of matter are emergent. So if we talk about, let's say, the color of a piece of metal, that's a property of many atoms. But if you take just a single atom of iron, we will not have the same color, if you wish. So that, in this sense, there are many properties of physics of ordinary materials that depend on the fact of depend on having many atoms. So, for example, water can be a liquid or a gas, and those are two configurations which are distinct when you have many atoms. But if you had one atom, you couldn't, or one molecule of water, you couldn't tell whether it's one or the other. So there is the idea that space-time is like this, that only emerges when you have many. I think the idea is correct, but in the sense that if you want a classical space-time that looks like what we have in the space-time around us, then it's emergent in that sense. But the idea is that if you had a small number of particles, perhaps you would have a very quantum mechanical space-time. And so if you are wishing to say that you are tolerating a very quantum mechanical space-time, as I think we should in a theory of quantum gravity, then I think it is possible that we have a precise equivalence. But the problem is the bulk theory is not as well defined as the boundary theory. So far, if someone wants to say that the bulk theory only makes sense when we have a large number of particles on the boundary, then we can contradict that person. Maybe I should explain. There is a concept I referred to here that I didn't fully explain. So the idea is that these theories that live at the boundary consist of particles, and they are similar to the theories of particles that we use for nature, for describing nature, except that there are kind of many different types of particles. So there is some number n of particles, particle types, that is very large. They're somewhat similar to the theory of strong interactions. So in the theory of strong interactions, is a theory similar to the theory of both electromagnetism and weak interactions. But the particles have a property which is called color. This number of different types of color is 3 in the case of the theory of strong interactions. And so, for example, there are 3 types of quarks and so on. In these theories that live at the boundary, you would need this number. There is a similar number, but it should be very, very large. So as large as the universe is in Planck units. So, for example, if you wanted to describe a universe that has the size of our universe, but let's say we had negative cosmological constant instead of positive, but with the same magnitude, then the number you would need is 10 to the 120. So it's a very large number.
Yeah. Well, I'd like to get back to conformal field theory and then anti-de Sitter space in a few minutes. But right now, returning to what you said about the equivalence of the bulk and boundary theories and descriptions in this duality here, restricting ourselves to black holes, you said that, the region of the well can be explained via a description of, I think, low energy D branes on the boundary, and that these are equivalent, but because the latter is lower dimensional and quantum mechanical and mathematically more tame, it's just easier and perhaps more useful to use this version for some reason because they're intertranslatable, but one is not fundamental.
That's right. It's more useful for questions about black holes and whether black holes preserve information or not. That's one application where the boundary description is more useful. There are other questions for which the bulk description is more useful. So, and that's a direction that's also been explored a lot. So for that, I need to say one more thing about this boundary theory, which is that the particles that live in this boundary theory are very strongly interacting. So they interact very, very much with each other. And this makes this boundary theories hard to analyze. But the bulk theory is somehow simpler to analyze, at least for certain problems. Like, let's say we don't consider problems involving black holes, but other problems involving gravity waves, or even with black holes, how gravity waves fall into a black hole and these type of questions. So those are questions we can easily answer using the Einstein equations. So the bulk gravity description. And so then this AdS CFT correspondence translates a difficult problem in the boundary theory to a simple problem in the bulk theory. So that's using this equivalence in a different direction. To learn there, what you're doing is you're using gravity to learn about strongly interacting theories. And you can use this to model systems in either nuclear physics or condensed matter physics and so on.
Well, moving back to some more fundamental questions, because I mentioned before, I mean, our listeners are all smart and curious, but they're not all trained physicists. So I think we should devote just a bit more time discussing anti-de Sitter space on the one hand, and then conformal field theories on the other. And this is very basic, but what is the difference between positive and negative curvature of space?
Right. Well, let's start with flat space. So flat space is perhaps most intuitive because our universe around us can be approximated at least by flat space. Then when we have a positive curvature space-time, including time, that describes an expanding universe, so some universe with constant expansion rate. Our universe is now kind of similar to that at very large scales, and will become even more and more similar to that simplest constant expanding universe, sometimes called the Sitter space. Now, an anti-de Sitter space is a universe that could be, well, it's time independent, so there is it's neither expanding nor contracting, but in some sense it expands when you go along the space direction. So if you go along a spatial direction, there is an expansion, let's say, of the time. Now, what this means in practice, a more pedestrian way, is to say that there is a kind of gravitational potential so let me explain this point a little better. So when we talk about curved space-time, what we mean in particular is that, for example, the flow of time in different locations could be different. So, for example, you are sitting right there, and there is some flow of time, let's say, in your chin, right? And time flows differently in the top of your head. And the reason that happens is that you are sitting in a gravitational field, and so time flows more slowly around your chin than on the top of your head. Now, this is a very, very tiny little effect that with the best clocks you could determine. I mean, with an atomic clock, the best ones can determine a height difference of a few millimeters, but it's a real effect.
And the difference is huge, though, between where we are now and the event horizon of a black hole, for instance.
Exactly. Yeah. So that difference becomes more pronounced the more compact and heavy the object is. So if you at the horizon of a black hole, the difference is, if you wish, infinite. So the time at the horizon, with this definition of time, if you're just sitting at the horizon, not falling through the horizon, time is not flowing, and so the difference is infinite. So that's what happens. Now, Now let's go back to anti-de Sitter space. So anti-de Sitter space, if you this is a very symmetric space, so you could be an observer sitting in anti-de Sitter space, and then what you would feel is that there is the time goes at a certain rate in your location, and if you go further out, it goes faster, and so you are like in the bottom of a big gravitational potential well. And if you throw any particle out, that particle will go out and then come back into where you are. So it's kind of the opposite of an expanding universe. In the expanding universe, you just throw out a particle, it will continue to go out and will never come back to you. If you have, in this space, everything kind of concentrates things back to you. And it's similar to a gravitational potential well. The simplest version is you are sitting at the bottom of this gravitational potential well, and the gravitational potential grows and grows as you go further out, without bound, so that the particle can never escape. So it will always bounce back and get back to you. So that's roughly how one could think about it.
My understanding, though, is that when we think about anti-de Sitter space, it's in a please tell me if I'm wrong here. It's in a vacuum state, so there isn't mass in it. And would this mean, though, that at any point, since it's so maximally symmetric, if at any point there were a particle and you threw it out, it would just come right back?
Yes, that's right. So if you're an observer just sitting freely sitting freely in that space, if you throw a particle, it will come back to you. You might have a friend who you can also think about the point of view of that particle that got thrown. It's just it's falling also freely, and that particle sees that you went out, right? You went in some other direction, and then you meet again. So the description would be similar from your point of view and from the particle point of view.
And then, with regard to conformal field theories, I mean, most of our listeners will be familiar with the term quantum field theory, in which quantum mechanics, special relativity, and classical field theory merge, and subatomic particles like electrons and neutrons are viewed as excitations of underlying quantum fields, but they may not have heard of conformal field theory. So what is the rough relationship between the two terms?
Well, a conformal field theory is a special type of field theory that has an extra symmetry, a symmetry under scalings, that the physics at different scales looks the same. Now, if you had a theory with massive particles, the mass of the particle sets a scale, and the theory would not be invariant under scalings, so it will not be conformal. Now, if you took something like the standard model and you went to very, very short distances, the theory is approximately conformal. So so that's an example. So we have these examples in nature. So if you take, for example, the theory of quantum chromodynamics, and you studied that the energies that we studied in the LHC, Large Hadron Collider, it behaves close to conformal field theory. It's not exactly conformal, but it's close. So that's roughly a conformal field theory. So it's a theory where you can approximate all particles as being massless. So there is no mass scale, and the interactions have constant strength, as constant as as a function of energy. This is not quite the case in the standard model, but the coupling constants depend a little bit on the energy, but they change slowly with energy. So it's close to conformal. And now, conformal field theories are easier to analyze because they have more symmetries. They also arise in other physical circumstances. So, for example, in systems that describe second-order phase transitions, at the phase transition point, the statistical physics, the statistical system that describes that situation is conformal invariant or scale invariant. So conformal invariance is a little more than scale invariance, but I won't get into the difference between the two. So let's just, for the purposes of this, let's say it's the same as saying that you have scale invariance. So scale invariance means that if you have some excitation of some size, you could also have a similar excitation of a bigger size, and it would behave in a similar way. So these conformal field theories are simple kind of field theories, simple in the sense that they have more symmetries, and they arise in variety of physical systems. Second-order phase transitions, quantum critical points in condensed matter systems, and let's say in nature at short distances.
Well, now that we have holography, anti-de Sitter space, and conformal field theories on the board, I'm ready to get back to the AdS CFT correspondence. And again, maybe just to summarize, make sure we're on the same page. Am I correct then that roughly the conjecture is that the holographic principle can be realized within string theory, and more particularly that a string theoretic bulk in anti-de Sitter space is indistinguishable from a conformal field theory in one less dimension on the boundary of that bulk?
Yeah, that's correct.
Okay, perfect. Then I think the first question that comes to mind that I don't think that we have addressed yet regards this word indistinguishable that I just used. And how is it that entities or processes in the bulk can be translated to entities and processes in the boundary, and vice versa?
Right. So the idea is that there is a kind of dictionary that, given some calculation you do in the boundary, there is some way of doing that calculation in the interior. The dictionary is not obvious and is not complete, so we understand some features of the dictionary, but not everything. So, for example, in certain cases, we expect that the black hole interior should be described from the boundary, but we don't know the precise dictionary. For other things, we know the precise dictionary. So basically, the closer something is to the boundary, the easier it is to describe, and the more precise the dictionary is. So yeah, that's roughly the idea. So the idea is that something that is very close, that is closer to the boundary, is described by a very small object in this conformal field theory. And as it moves away from the boundary towards the interior, it becomes a bigger and bigger object.
Mm. This is totally unrelated, but I'm going to draw it back in a second. But I saw that you have Italian and Argentinian citizenship. Are you from Argentina?
Yeah, I'm from Argentina, but
you
my
just have Italian ancestors?
Yeah, I have Italian ancestors.
Okay. Well, here was where I was leading with that. And so the bulk theory, as we've said, is much less tame than the boundary theory. And I'm going to draw an analogy here to Spanish and English. And so even if, let's say, we're both English speakers and we don't speak Spanish, even if we did have a dictionary that translated from words from English to Spanish, and so we knew what every word in English was, let's say it's the boundary theory, it's the simple one for us. If we translated it into Spanish and we knew the equivalences, we still would have no idea how the Spanish language worked. Is that a rough analogy to? I mean, we know more about Spanish if Spanish is the bulk theory, but even though we know the equivalences, that doesn't completely mean that we understand the bulk theory. Is that?
Yeah, it's something like that, but it would be like having an incomplete dictionary. Let's say you have an incomplete dictionary, some words missing. So maybe from context you can try to figure out what they mean, but there will be certain words that you don't know what they mean. So you have to work harder. You have to look at bigger and bigger context in order to figure that out. That's a very rough analogy.
Okay. And then one other thing that I wanted to dig into at the beginning of our conversation, you mentioned that string theory provides us with some very useful toy models for dealing with quantizing gravity. And in the AdS CFT Correspondence, that original paper, my understanding is that you worked in a space called AdS 5 by S5. And I'm wondering, I mean, this is not our universe. It's just a model. And I'm wondering why my first question is, I mean, can you explain to us what this space looks like, and then why you worked with it for this paper?
Well, string theory is simplest in 10 dimensions, or spacetimes that are weakly curved in 10 dimensions. I consider this spacetime because there is a solution of one of the string theories that is precisely a 5-dimensional sort of anti-de Sitter space times a 5-dimensional sphere. So you can think of the 5-dimensional sphere as some internal space, and then you have the anti-de Sitter space that we were talking about before. Then that space has many symmetries, and the boundary theory is a 4-dimensional theory. And it's a 4-dimensional theory which is conformal invariant, so it's scale invariant, and again has various other symmetries that we're not going to get into. And it's very similar to the theory that describes quantum chromodynamics. So it's, if you wish, a version of quantum chromodynamics with some particular matter content that makes it scale invariant and have these additional symmetries that I'm not discussing. And so it's a very symmetric, both the bulk and the boundary are very symmetric. And they are the only somehow known theories with those symmetries. So that kind of facilitates, one of the arguments for the correspondence is, for the duality, is that the two sides have exactly the same symmetries. And this 4-dimensional theory had been studied before as because of these symmetries and various nice properties that it displays, like duality between electric and magnetic charges and so on. So that, well, maybe I should, I'm doubting whether to get into the precise symmetries of this theory or not, but it has a symmetry that is called supersymmetry. It's a symmetry that relates so-called particles that are called bosons and fermions. And it has the maximal amount of this type of supersymmetries. So the maximal amount that the field theory can have, that quantum field theory can have. And so such theories are very constrained. They're sort of Lagrangian, or the laws of physics for such theories are completely fixed in terms of the choice of so-called gauge group, which is like some number of colors, similar to what happens in chromodynamics. And then there is a coupling constant. So that completely specifies the theory. So it was a particularly simple case. And then later people found some other examples, well, in various dimensions. So even in the original paper, I had also examples in other dimensions. But this example is kind of the simplest in certain sense because of the many symmetries it has. And is one for which a lot of calculations were done, and there is a lot of precise relationship. Well, many things were checked. Let me just try to explain one of them. So according to this, so in theories that are like chromodynamics, that have a large number of so-called colors, the particles of these theories have a color and an anticolor, and they can form chains where the color of one is correlated with the anticolor of the next, and so on. So they form a kind of necklace of particles, and they behave. These chains behave a bit like strings in the bulk theory, the same thing happens in ordinary chromodynamics, and where they behave like strings in our 4-dimensional world. But in this case, the strings are in this 5-dimensional anti-de Sitter space. And there were mathematical techniques that were developed in order to show that we can go from these chains that you have at weak coupling in the boundary theory, where each particle moves independently. And as you make the coupling constant stronger, the chains, sort of the motion of these particles becomes more correlated, and in such a way that it can be described by a string that lives in the 5-dimensional, or more precisely 10-dimensional bulk space. And this is something that's been shown mathematically. So it's I would say this is great evidence for this duality, or for the correspondence between the two theories.
Well, there are a lot of things there that I want to ask more about, but the first thing is just at the beginning of your response now, and please correct me here if I'm wrong, or just making little mistakes, but restricting ourselves to the five-dimensional anti-de Sitter space for a moment. You said that string theory works best in 10 dimensions, and I believe that M theory works best in 11 dimensions. And my understanding is that for the vibrations of strings and various branes to produce the properties of the particles that we observe in the standard model, they require these extra compact 6-dimensional Calabi-Yau shapes in which to move. And what I'm wondering is how, if the theory requires, or theories require 10 or 11 dimensions in these Calabi-Yau shapes, how the bulk theory can be, well, we don't need to get into the bulk theory yet, but how string theory can be emulated in the 5-dimensional anti-de Sitter space.
Okay, so I think string theory can be used in various ways. When we're talking about trying to reproduce the standard model, that's sort of one objective we might have. In order to, it's of course an interesting objective to try to understand the physics of our own real world.
Very good point.
Yes. So now when we are talking about this AdS5 and this duality, this basic example of the duality, we are not trying to reproduce gravitational physics in 4 dimensions with our matter content. We are content with having gravitational physics in 10 dimensions, on a space which is AdS5 times S5. So it's a 10-dimensional space-time. It's something we can understand easily, well, relatively easily in string theory. And that's the same as this theory in 4 dimensions, this other theory of particles in 4 dimensions. So before, for example, when I was describing the way that strings emerge from the chain of gluons, the gluons are these particles in this version of chromodynamics. When you have this chain of particles, the chain of particles lives in 4 dimensions, but the string that they describe lives in 10 dimensions. So yeah, that the fact that it's 10, it's related to the particular set of particles that we have. We have gluons and then some other fermions and scalar fields.
Right. And when you say that reproducing the standard model is only one use of string theory, is this also an allusion and maybe implicit reference to the multiverse, and that some string theorists would like to be able to model all possible universes in string theory?
Yeah, that's right. So it might be that for understanding aspects of cosmology, we need to consider not just our own 4-dimensional world, but many other possibilities. Here, that's true, but it's, again, orthogonal to the discussion. So this is one example of the duality, and it uses this particular universe. We could have other examples which use, 4-dimensional anti-de Sitter instead of 5-dimensional anti-de Sitter. There are various things we could do, and people have studied all these other possibilities. It's a large number of other possibilities. we don't understand the full set. I mean, we cannot give a complete list of anti-de Sitter spaces where the duality works. We think it should work for all of them, but we don't have even a complete list of possibilities. So I should perhaps say something at this point, which is related to string theory and a bit orthogonal to the quantum gravity discussion. So I mentioned in the beginning of the interview that string theory originated as a theory of strong interactions, and this had its origin in the fact that strings were observed in particle collisions. So strings are things that exist in nature, and they were observed in particle collisions at colliders. And when experiments were done at higher energies, it was realized that these strings were somehow made out of the gluons, some other more elementary four-dimensional particles. But this shows that, first of all, that strings are real. There is a version of strings that exists. Second, it was realized that these strings would be weakly interacting and more similar to the strings of string theory if you took the number of colors to be very big. So instead of 3, very, very large, and already perhaps 3 is fairly large for these purposes. And so people had the question of what kind of string theory describes these strings that arise from four-dimensional gauge theories, right? And it wasn't clear that it was the same as the 10-dimensional string. It was something, there seemed to be a contradiction because the strings we understood are in 10 or more dimensions, and these other strings seem to live in 4 dimensions. But it was realized by Polyakov that these strings really should be viewed as living in at least one more dimension. This basic example of the duality is a concrete realization of this idea that the strings of chromodynamics live in one more dimension. This idea is 5, or really 10 dimensions in this case, live in more dimensions, and it's a concrete realization of this idea that the strings that are similar to the strings of strong interactions are actually connected to the ordinary strings of that we were using for quantum gravity. So now we could say, well, let's forget about quantum gravity. We could say, well, if my interest is, if you're a researcher just interested in 4-dimensional theories, but you are interested in understanding theories, for example, at strong coupling, then you can use this 10-dimensional description with AdS 5 times S5 as a toy model for a strongly coupled field theory, and it was used in this way. So from this point of view, you don't care that the interior is not the standard model and so on. What you care in that case is that the boundary theory is somewhat similar to the standard model. You're not trying to, similar at least to the theory of strong interactions.
I know that this is orthogonal, as you said, but it's really important and really interesting. And I was at first surprised to hear you say that strings were observed in colliders because, well, before I say because, but they're not the strings of string theory. They're the gluon necklaces you were referring to when we were talking about conformal field theory.
Yes, but the duality shows that they are not so different.
The duality may show that they're not so different, but my understanding is that the general physics community does not think that strings have been observed. The string theoretic strings have been observed.
No, they don't. But probably that's a true statement. But I think intellectually they are rather similar. And I think people have been trying to take the large N limit of quantum chromodynamics, so large N, and find some strings there and see how different or similar they are. So the correct statement is that if you replace quantum chromodynamics by another theory that you add extra matter fields, then it becomes this highly supersymmetric version of quantum chromodynamics. And then for that version, the strings are really the strings of string theory. So they are closely related. They're not completely unrelated. So yeah, so from a theoretical point of view, I could say, well, and those strings are the strings of colliders are relativistic strings. They are, similar to the strings of string theory.
When you say relativistic strings, you're referring to the 4 dimensions?
Yes. So okay. Why are the so let me try to explain the difference between a violin string and the strings of string theory. Okay, both are strings. The violin string has a very large mass per unit length compared to its tension. So MC squared, or MC, so it's much larger than the tension. For that reason, the waves that propagate along a violin string go at a speed less than the speed of light. So a relativistic string is one where the mass per unit length is essentially the same as the tension, up to factors of the speed of light and so on. And so then for those strings, a perturbation, for example, would move at the speed of light along the string. And the ones that are observed in the collider are the same as the second one that I mentioned, and those are also the ones of string theory like that. There could be also something people call cosmic strings, which would also have this property. They might arise they must arise as some kind of soliton in quantum field theory. So so that's what I would call a relativistic string. The strings of fundamental string theory, or maybe I should say weakly coupled string theory, the ones that are easy to understand, are strings that interact little when they cross, so they can just cross without reconnecting very easily.
And my understanding is that cosmic strings can really grow to, or have grown to, cosmic proportions. And if I'm recalling correctly, Ed Witten has a very funny quote where he says something to the effect that how funny would it be to confirm string theory by looking through a telescope rather than something like the LHC.
Right. Yeah. So that's a possibility. So it could be that cosmic strings could be either made of other particles, like solitons of field theory, or they could be also fundamental strings. And I think it was referring to the fact that they could be fundamental strings, and they would have slightly different properties. So this fact that when they crossed, the probability of reconnection could be different. But so far, cosmic strings have not been observed. But it's one of the things people are looking for. And would be nice if the universe is kind enough to provide us with very big fundamental strings. It would be really wonderful.
Well, returning to from our tangent to the main thread of our discussion, and one of the last things you said was that you chose to use the 5-dimensional anti-de Sitter space for the correspondence because it was tame. The symmetries were neatly aligned between it and the conformal field theory, the boundary theory, and so on. But then this raises the question, if one of the goals is to explain our universe, what ensures the relevance of this result? Or maybe not ensures, it's still a conjecture. But what leads you to believe that there is, or there might be, a corresponding correspondence between our potentially 11-dimensional bulk and the boundary?
Right. I think the idea would be that there would be a similar correspondence, perhaps. It's not clear where the boundary would be in our universe. So the most natural boundary that our universe would have would be in the very far future that will expand. And in some sense, there is a boundary which is 3-dimensional Euclidean space. And so maybe there is another.
The universe is 4-dimensional?
Yeah, the universe is 4-dimensional, and it has a 3-dimensional boundary in the far future. So you can think of that as some surface that at some moment in time in the very far future. So before we were talking about the boundary as some place in space very far away. In an expanding universe, we would say, well, some spatial region, some moment in time at very late times. And it could be that our four-dimensional universe can be defined in terms of certain statistical system in 3 dimensions. So field theory in 3 dimensions. But we don't know any example that has a gravity, Einstein gravity dual. That there are examples that have are related to weird theories of gravity, strange theories of gravity, with lots of massless higher spin particles, where this seems to be true. So one would need to generalize the correspondence to this case. This could be one way in which it could be generalized. The other possibility is that there is some kind of quantum mechanical system that describes our observations in all the way up to the cosmological horizon. That's another possibility that people are thinking about. But we don't have some examples. So in the AdS case, in some sense, we were lucky by this discovery of Polchinski of these objects called D-branes that acted as bridges between the field theory and the gravity theory. And we don't have similar objects or they are not known, that could help us in this cosmological situation.
The first possibility you mentioned with the boundary being far in the future, it's hard for me to wrap my mind around this, particularly because wouldn't the bulk, if we're still using this hologram metaphor, wouldn't the bulk have to be a projection into the past for us to exist now? If there is no boundary now and the boundary is in the future, but the bulk is a projection from the future.
In general relativity, the universe, it continues to the future, and you could consider what will happen in the future. We somehow are at some point within that 4-dimensional universe. We're at some point in time, and
if you're taking like a block universe sort of picture. If you're taking sort of like a block universe sort of picture, everything exists.
Yeah, so it has this further, and we are living in some kind of slice at some moment in time. So we would be some object in that boundary. So I don't want to talk too much about it because we don't have concrete examples.
Sure.
There isn't a completely obvious reason why it could not be true.
But then maybe we don't have to keep talking about this too much more, but just to wrap my head around it, just as there are...
Let me make one little point about this, which is the fact that if such a description existed, then we would have something well-defined in the future, and the fact that there is a singularity in the past or something like that, which just means that the bulk 4-dimensional picture ceases to emerge somehow in the bulk. But there is still a well-defined description in the infinite future for anything we could calculate at that point. I should mention that, it looks like this description is a little weird, but when we look at the very early universe, we are somehow looking at the projection of, we're looking at the similar slice, if you wish, or similar moment in time. So the early universe, there were things that were happening in the very early universe that left their imprints in the universe we observe today. So, for example, when we say that the inflation predicted some fluctuations and imprinted some fluctuations, which we now see through the cosmic microwave background, that surface that we see that we see with fluctuations far away, is a bit like this. The surface of the far future of the early universe. So from the point of view of the early universe, that is in the far future. And by looking at the correlations, the statistics of fluctuations, whether it's up or down, and how they are distributed in space, we can figure out what was happening in the very early universe. So we can say, well, there were particles being created, or maybe there could be interactions between particles, and so on. So we can reconstruct, in principle, we can reconstruct the physics of that very early universe by looking at this sort of cosmological observables.
So when we look at a star that's in the past, what we're seeing is part of, it might be thought of as the surface of a rough sphere of photons whose surface is determined by the geodesics that those photons traveled.
Right. Yeah, for the case of a star, the translation is a little more direct, but...
Oh, well, very, very interesting. But what I was going to ask before you added that point, and I'm sorry for harping on this since you've mentioned that we don't have a fully developed theory for this, but I was wondering if one way of making sense of this boundary being in the future but projecting into the past is, I mean, we're familiar with non-local interactions in space from quantum mechanics through entanglement, for instance. It's not that much of a stretch to think that there could be non-local interactions through time in the case of the boundary, and the boundary being in the future and the bulk not.
Yeah, in quantum mechanics, I wouldn't describe them as interactions. So we have correlations which are non-local and sort of stronger than classical correlations. So that's entanglement. And yeah, so in the AdS case, there is a radial direction, a space-like direction that is emergent from the boundary, right? And the idea is that similarly in the future there would be an emergent direction which now will be time-like. Would be time. So yeah, but we don't have very good ideas for how this would happen, or what properties, so that you would need perhaps some special properties about this statistical field theory to have a time emerge. Yeah, I should mention, you mentioned entanglement, and one of the themes of recent developments is to highlight the importance of entanglement in the construction of space-time from the boundary theory. So you have, in the boundary theory, the vacuum is a highly entangled state, and the bulk reflects some properties of this entanglement.
Mm-hmm. Right. Eric Verlinde, I know, is working on emergent gravity that emerges from entanglement entropy.
Yes, and there is actually this been, so we mentioned in the very beginning this formulas of Bekenstein for the entropy of black holes, and now we have a new formula that was originally developed by Ryun Takayanagi and then improved by various other people, that calculates another kind of entropy of a black hole. So the entropy that von Neumann discussed is an entropy that calculates the sort of quantum information available or contained within a system. So if you have a quantum system, sometimes it might be in a so-called mixed state, not in a pure state. And there's a quantity that characterizes how mixed, how many possible quantum states you have. And that is the von Neumann entropy, or sometimes called fine-grained entropy. Now, this is in general different than the sort of Boltzmann entropy or thermodynamic entropy of a system, especially when you are out of equilibrium. So for describing, for example, a collapsing black hole or situations like this which are out of equilibrium, you get the difference between these two entropies. And we have a sort of area formula for each of them, and it's been quite useful to think about this direction. So in the same way that the Bekenstein formula told us many things about black holes, this other formula is also telling us interesting things about the black hole, and in particular about the black hole interior, because the area is also, the formula also computes the entropy as some area, but it's not the area of the horizon, it's the area of some surface in the interior that you need to determine. So it's telling you some information about the interior.
do these two conceptions conflict at all, or are they simpatico?
No, they are compatible with each other. So it's just that normally most physicists have heard only about they know one definition of the entropy, and normally this distinction between the two types of entropy is not definitely it's not relevant for a system in a thermal equilibrium, but that has equilibrated over a very long time. But it is quite relevant for systems that are out of equilibrium.
Well, that's very interesting, because then it's quite like the AdS CFT correspondence, in that two descriptions of the same phenomena can be useful in different contexts.
Yeah, well, this is more elementary, I would say. So even for simple systems, this idea of thinking about the two entropies is something that people have discussed. They discuss a lot in the condensed matter physics literature and so on. But it's important when you consider out of equilibrium situations.
I know that you wanted to get away from this, but this is, I promise, the last question that I will ask about the boundary. And you can also totally decline to answer it, because it opens up a huge can of worms. But I could conceivably understand a boundary far in the future. But at one point you said there might be a boundary infinitely far in the future. And that's difficult for me to wrap my mind around physically.
Well, let's say infinitely means very far.
Okay.
There are no infinities in physics. It's always some very far. There's always some idealization. It means that it's very far compared to other timescales that you are considering in the problem.
Okay, sure. No, that makes more sense, because I always hear that whenever an infinity crops up in a physics equation, it means that something has gone wrong somewhere.
Right. No, this is not. This is just simply reflects an idealization. It means much larger than other things.
Well, then, okay, moving on from considerations of the boundary, and please feel free to tell me if you're sick of talking about the AdS CFT correspondence, and we can move to something else. But specifically, why is it so important for quantizing gravity, the fact that we can describe gravity with a conformal field theory?
It's important because if you accept this duality, right, or this correspondence, then it tells you what the answer is. So it tells you that if you were to quantize gravity, you should get something identical to this quantum field theory. So if you wish, it's a bit like an oracle. This is what you should get if you were to quantize gravity. Other people might think, well, this could be like the definition of gravity in AdS. So it gives you a complete solution of a theory of quantum gravity. And then you can explore its properties and try to learn some more general lessons. It's limited because it's limited to anti-de Sitter space. It's limited because the easy elements of the dictionary are those that involve observations very far away. One would like something more. One would like to be able to answer what happens to an observer that approaches the black hole singularity, for example, and questions of this kind. And it's possible that by understanding the dictionary more, we will be able to answer those questions. So it gives us a kind of non-perturbative window into quantum gravity. So the traditional definition of string theory was what we in physics call perturbative. So there's some coupling that is small, and then we compute corrections in that coupling constant. And so we could, in principle, compute to any order, but we get some kind of approximate description. The boundary theory gives you, in principle, an exact description. So it shows that if you accept it, it shows you that quantum gravity. So in these situations, it's described by unitaries, respects the laws of quantum mechanics, at least for observers who measure things from far away, the laws of quantum mechanics are unmodified. So it answers some conceptual questions of this kind. And also, as anything, you would like to extract as much information and lessons from it as you can. And people are busily trying to do that. And doing that.
Yeah. You said that it evolves unitarily, and I hadn't realized before having some of these conversations just how fundamentally quantum mechanical string theory is. And I imagine that demonstrating its equivalence in this case, or intertranslatability from the five-dimensional anti-de Sitter space to the conformal field theory, really buttresses this notion that it is fundamentally quantum mechanical.
Yes. Mm-hmm. Yes, at least for observers who are measuring things from far away, which are not subject to very strong quantum gravity fluctuations. You could still entertain the possibility that perhaps for observers who are falling into the interior of black holes, there is some modification of quantum mechanics that we cannot rule out. Might be possible.
And I said that I think I've kept true to this, that I was going to dig into everything that you mentioned in your initial sort of summary of the issue. But now I wanted to dig into another word that you used, which was emergence with regard to space. And I was wondering if this result to you, because I'm sure that there are many different opinions, if it suggests anything about the nature of space and time, and whether on the one hand they form a background for physics, or on the other hand they emerge from more fundamental physics. And one of the reasons that this question arises for me is that if we can sort of translate from one theory to another in different dimensions, and no one description is primitive, they're just equivalent, it might suggest that space and time are not determinate.
Right. Well, let me try to answer this question, or address this question first, assuming as little as possible. So we know from just the Einstein theory that as we go to shorter and shorter distances, the quantum effects become more important. So space-time is somehow more fluctuating, and so on, as we go to shorter and shorter distances. There's some distance called the Planck scale at which the fluctuations become very big. The theory becomes very difficult to analyze. Now, in physics, we think that the fundamental description is determined at short distances. So at least in the standard quantum field theory, that's the case. So for example, for the theory of strong interactions, the nucleons interact somewhat strongly with each other and so on, but you go to shorter distances, you have the gluons, and that's the basic description. So in gravity, you might naively think, okay, yeah, the description should be fixed at least the Planck scale, but there the gravity, space-time itself is very fluctuating. So that would suggest that it should be replaced by something else, that the correct theory should be formulated in terms of some other notion, and that space-time, at least the usual continuum space-time that appears in general relativity, might be some approximation. So that's something you could say without talking about string theory or holography or anything. And people were trying, for example, Regge tried to construct this, some kind of version of this by thinking about small triangles and so on. So that's a very general point. So that's a reason for thinking that space-time should emerge from some other description. And just to harper a little more on this point, to insist more on this point, for example, you can consider the history of the theory of weak interactions. So the weak interactions were described by something called the Fermi's theory of weak interactions. It was some theory. And in this theory had a scale at which the theory predicted that it would fail. Instead of a Planck scale, it was a scale of the order TV. So the scale is currently explored by the Large Hadron Collider. So people in principle knew that the theory had to fail at that point and maybe replaced by something else. And indeed, it was replaced by something else before you got to this point, which is the Weinberg-Salam model, or the standard model, in which there are new degrees of freedom, like the W boson. So there are some other particles. There are new particles, W boson, Higgs bosons, and so on. And then all those particles at low energies, they reduce to the Fermi theory. So you could say that in some sense, the Fermi theory emerges from the more complete standard model that we now know. So the gravity theory has properties, Einstein gravity has properties similar to that of the Fermi theory, in the sense that the interactions grow at short distances. Again, so these are two very general. I try to explain this very general reason why we expect a slightly different description at short distances. One is just simply because the interactions become large. The second was a historical example of the theory of weak interactions. Now, in gravity, there is something more funny that's supposed to happen. So something weirder that's supposed to happen, which is that the techniques that we normally have for exploring short distances, we expect them to fail in gravity. So what are the techniques we have to explore short distances? It's basically colliding particles at very high energies. So the higher the energies, the closer these particles get, and the shorter distances they are exploring. But in gravity, once you start colliding elementary particles at the Planck scale, they can start forming black holes. And if you now increase the energy, you will not be exploring short distances. All that will happen will be that you will form a bigger black hole, so which are bigger. So you're not really exploring shorter distances. So somehow, in gravity, it looks like these shorter distances somehow do not exist in some way, or they don't exist in the same way that they exist in a theory of ordinary particles. So that's some other indication that something stranger is happening with gravity. Again, here I haven't used string theory or anything. It's just these are just properties of Einstein gravity. And in holography, there is something else that is going on, which is that the fundamental description lives at the boundary, not in the interior. So indeed, in that description, definitely space-time is emergent from, at least if you think that the fundamental description is the boundary theory, then the interior space-time is certainly emergent. So it's a concrete example of how space-time could emerge from some more fundamental description. The more fundamental could be the boundary theory, where that bulk space-time is not even there. So that is a more concrete, perhaps, example of how this can happen.
Oh, thank you. That was really helpful. Just this is an important detail, but since black holes are so fascinating and people don't often talk about and might be unfamiliar with microscopic black holes, is the reason that they arise at these small distances and high energies that the contacting particles in these collisions become so close and the compound that arises from them so dense that their gravitational force is sufficient to prevent photons even from escaping? Is that
yes, absolutely? Yes, you're absolutely right. Yes, that's correct. So you're concentrating a large amount of energy in a small region. That's whenever that happens, you can form a black hole. Now, in order to form a very tiny little black hole of order of Planck's mass, you need to have a collision at exceedingly high energies of order of the Planck scale. So you need to concentrate a lot the matter. So if you don't have very dense matter, like you have nuclear densities of matter and so on, which is pretty dense, but something achievable in a neutron star, then you need a very big black hole, very, very large amount of matter. And you can only in that way make very big black holes of order kilometer in size, few kilometers in size. So that's the low density of nuclear matter compared to the Planck scale is what explains why the black holes that exist in the universe are so big. But in principle, as solutions of Einstein's equations, you could have black holes of any size. And so you often speculate that perhaps some processes in the early universe might have resulted in microscopic black holes or black holes of smaller masses. None of them have been observed yet, but it's something that is reasonable to speculate about.
And is this why, getting back to something you said much earlier in our conversation about D brains, is this why certain D brains resemble black holes because they are so dense and highly energetic?
Yeah, that's right. Yeah, you could say that.
Okay, great. And then, well, finally moving on from anti-de Sitter space, are there generalizations or similar correspondences between de Sitter spaces and conformal field theory?
Yeah, so the de Sitter space is the question of the expanding universe. So
right, which seems like it would be more relevant.
Yeah, no, this is more relevant. I mean, the de Sitter, it would be much more interesting to have a de Sitter CFT correspondence than an AdS CFT correspondence. And I think everyone recognizes that, but the problem is we don't have an example. So normally people say, well, in research you somehow have to compromise. So you might not solve the problem you really would like to solve. You solve another problem, a simpler problem, and you hope maybe at some point you'll be able to solve the problem you really want to solve. But yeah, so the problem we really want to solve, we're most interested in, is the de Sitter case.
Mm-hmm. I think
maybe you can say that we made a sign error, right? We solved the problem with negative cosmological constant. We should have solved the problem with positive cosmological constant.
Well, we'll get to that in a moment because I don't think the cosmological constant has come up in our conversation yet. But I think I might have read that Andy Strominger, we didn't talk about it. I think I might have read that he conjectured or was writing about the possibility of a DS-CFT correspondence.
Yes. He wrote several papers about this, and he actually came up with this example I mentioned with the weird theory of gravity, together with other collaborators. So it might be that it's just a weird theory we haven't found yet, and maybe in the not so distant future people might find the theory.
How might this have cosmological or implications for our understanding of cosmology that relate to the cosmological constant and the expansion of the universe?
If we understood, at least we would, if we understood that there is a possible description of the physics in terms of a bound of some theory in 3 dimensions, then we would at least have perhaps a conceptual understanding of what happened in the very beginning. So where the current theory fails, right, where there was an initial singularity, the description in the boundary will not be singular and will allow us to give a complete description. So that's one conceptual point. Now, I think perhaps your question is more like, is there some experimental prediction we could make from this description? Now, since we don't have the description yet, we don't know how constrained it is. I mean, normally to make experimental predictions, you need your theory to be very constrained enough so that there are relations between possible observations. We don't have that yet. So we don't have an example, so we can't. I think we can't answer your question. I think you also referred to the question of whether we would be able to explain the cosmological constant. Now, in this type of descriptions, the cosmological constant is related to the number of fields you have in the boundary theory. We would need to have a huge number of fields of order 10 to the 120. I mean, this 10 to the 120 is just the ordinary number that is mentioned in the context of the cosmological constant. So it would come in that number of fields. Now, why should we have that number of fields and not a smaller number of fields? Maybe we won't be able to explain, maybe we will. I think one could say that there is a version of the cosmological constant problem in AdS CFT or DSCFT, which is to explain why the universe is local, why we have local physics at distances much smaller than the radius of either de Sitter or anti-de Sitter space. So that is something that probably requires perhaps it requires some special physics at the boundary. And so it's likely that there might be a translation between the bulk cosmological constant problem and some problem in the boundary theory.
Well, with at least some of the time remaining to us, I think we've covered the basics of the AdS CFT correspondence, and you've answered my confusions about it that I wanted to get sorted out. But now, over the past 25 years, since I think it was about 25 years ago, almost exactly, that you conjectured the correspondence, how has it guided and impacted research in string theory? I know that's a big question, but if there are any few directions.
Well, maybe I should say a few things. So there were people, of course, generalized and found other examples. I mentioned the mathematical formulas that prove or see this transmutation between change of gluons and strings. And there are other developments in that direction of getting more evidence and convincing ourselves that this works. Okay, that was one direction. Another direction was using it to model other physical systems. So perhaps systems in condensed matter or nuclear physics. And this had some impact in those systems, but it also has some impact in us in the sense that this conversation somehow led to questions about, helped us understand the correspondence better, and also maybe ask questions we wouldn't have asked otherwise. The most interesting question of this type is that in condensed matter physics, people sometimes were interested in understanding the entropy of regions of some region of let's say some material, and this led to this Ryuta-Kanagi formula that I was telling you about. And they somehow, even though it came from sort of a condensed matter question, it took a life of its own and became very important in our field, in the field of understanding holography in particular, and this AdS-CFT duality. So there were ideas of quantum information that came in and helped us understand aspects of holography, ideas of, for example, quantum error correction, some analogies between quantum error correction and this holographic map or dictionary between the bulk and the boundary. And perhaps it culminated with, one very big highlight was a couple of 4 years ago, a computation of a new way of thinking about the entropy of Hawking radiation, where you can show that the entropy of Hawking radiation does not increase, as Hawking said, but it after the black hole evaporates, is something very small. So it's consistent. So it's consistent with unitarity, and it's a way of computing Hawking radiation using this formula with the area, this von Neumann entropy formula, which I referred to. So that was very interesting because it gave a way to gave a result that is consistent with unitarity without using any duality, just purely from the gravity point of view. So this is an example where somehow the duality was useful for discovering a property of gravity that could have been discovered, years ago without, in the end, not making any reference to the duality at the very end. So somehow you can view the duality act as a kind of bridge or scaffolding that helped develop some of the concepts, but at the end you could just remove it and just make the statements purely in the theory of gravity, just using gravity. so that's and this has happened with some other examples, especially in this connection with condensed matter physics. There was one that I like, but I don't know how much detail. But if you want me to go into detail, ask me.
Yeah, please go into detail.
Yeah. So it's been observed that black holes, when you look at low energy modes or long distance modes, they behave a bit like hydrodynamic. They're governed by the laws of hydrodynamics at let's say low energies. And in the correspondence, people then looked at some black holes and they tried to match to hydrodynamics on the boundary, and it did not match. So it did not work. But it was understood that the reason it wasn't working was because people in the equations of hydrodynamics, they were forgetting some terms that are important in theories that have anomalies. So anomalies are a type of funny realization of symmetries in field theory, in quantum field theory. And then once you realize those terms could be there, they could be there. Well, they are there in the case of the systems that are involved in the duality, but they could also be there in other, let's say, condensed matter systems that have nothing to do with the duality or the examples of duality of the gravitational holography. And so this led to a focus on this type of effects and the new hydrodynamics associated to these effects. And so if you are interested in just that, you don't need to know anything about the duality, but the duality was useful for discovering these effects. Again, another situation where it acted as a kind of scaffolding that allowed us to discover something, but then whatever you discovered was a general lesson. So this is the advantage of having somehow a non-trivial, concrete model that you can study and theoretically. Well, there it acted as a theoretically interesting toy model where you could, use it to discover new things. And then there were other examples like this. I could go on with examples of this kind. Okay, so so those are. Well, I guess you asked me to list a few ways in which it was influencing current or influencing the research in string theory. So I mentioned understanding the duality itself better. I mentioned the connections with quantum information and learning more about black holes, lessons that then are even independent of the duality. And I also mentioned the applications to condensed matter and lessons that were learned through that.
Mm-hmm. And I had been planning to ask whether or not the AdS CFT correspondence related back to black holes. Since it emerged out of black holes, it just seemed right that it should relate back to it. So I'm glad that it did. It
did, yeah. I would say these developments in the last few years were very centered on black holes. There were other developments I mentioned briefly before that there is a system inspired by that arose from condensed matter for condensed matter reasons that displays also a form of holography, and so a connection between. It's a very simple quantum mechanical system that is related to extremal black holes. So black holes, similar to discharged black holes, we started the discussion from. And this led to a better understanding of the quantum mechanics of those black holes, certain interesting and calculable quantum mechanical effects that, thanks to this model, were identified and understood. Now, of course, they could be understood even regardless of this model, but this is an example where, having a concrete model helped understand these effects.
And then the last thing that I'll ask about this line of research is we did touch briefly on the DS CFT correspondence and how this line of research might shed light on expansion in the cosmological constant. Are there going forward any other big problems that haven't been answered yet that you think this line of research might contribute to, like perhaps that initial problem that started the conversation, like with explaining the Big Bang?
Yeah, if you ask me for kind of roadmap of what might happen in the future, maybe I would say that perhaps we'll understand the interior of black holes, and then after understanding the interior of black holes, we might understand the beginning of the Big Bang, or the initial singularity, or whatever happened before inflation. And so that would be something. But it's hard to make predictions, especially about the future. There is one topic we didn't discuss that I think is also interesting. So I mentioned a little bit the connections with quantum information, but there is something interesting, which is the fact that with the advent of quantum computers, it might be possible to do quantum simulations of these strongly interacting systems that have a gravitational description. And this might lead us to new insights about quantum gravity that we might not get, because we are limited in our research on quantum gravity. We are limited by the lack of experiments.
Right.
And these quantum simulations are a form of experiment on a kind of synthetic version of gravity. It's not really the four-dimensional gravity, but you could simulate sort of systems that have gravitational description, and we might perhaps learn some interesting questions, raise new questions we haven't asked before, and give us some insight. So I think that will become a new tool that, it's not in the very near future. It's something that might happen hopefully before, I don't know, maybe in 20 years or something, this might become a reality. But
that's very fascinating, though. So the experiments on string theory are limited by the extraordinarily high energies that would be required, I understand, but you're saying that the advent of quantum computing would mean that we have sufficient computational power to simulate some of these things that we can't
to simulate, and it will help us understand the theory better. So it would be a new tool that we could use to understand the theory better.
Well, the absolute last thing, one curiosity that we briefly touched on that I'd be remiss not to ask you about, it's more high level, but since this has come up on so many episodes, is the relation of string theory to the multiverse and fine-tuning. And fine-tuning, I think, is one of those very big and natural questions that arise when you start thinking about physics more. And I'm wondering if you're one of those physicists who thinks of the multiverse and string theory's relation to it as something that can help us make sense of fine-tuning.
I think it's something that seems to make sense of the fine-tuning, in the sense of providing, so the idea is that there are many possible there are many possible internal six-dimensional spaces or configurations, and there are many possible four-dimensional laws of physics. And there are some fine-tunings that are necessary for perhaps our existence, or for physics to be as it is here. And then we could perhaps explain them by saying that, if they were not possible, physics would be so radically different that maybe life might not be possible. Now, that's a long chain of reasonings for trying to explain this fine-tuning, but at the very basic point is that by having many possibilities, you have at least the possibility of accommodating our universe. That's a zeroth order statement with its fine-tunings. And perhaps even explaining those that are very crucial for our existence. I should say that this has a dark side. So let me just mention the dark side. The dark side is that if there are so many possibilities, it might be harder to make a prediction, in the sense that the connection between the fundamental theory and the physics of the four-dimensional world, because of there are so many possibilities, could be very complex. And now, hopefully there will be a way to surmount this dark side. But it's that's a feature. But it seems to be a feature of the theory that it contains many possible solutions. So whether we like it or not, some people say, "Oh, I don't like the fact that there are so many solutions." Well, that's what the theory is telling us. But so we have to accept it. At least from string theory, you have all these possibilities. You could say that even regardless of string theory, the fine-tunings might be a little hint that there might be different possible four-dimensional physics. This is a weaker argument, but
I think that something I heard, a quote maybe, was something to the effect that, referring to this dark side, is that what was meant to be a theory of everything has become a theory of anything, and that this is what leads to it loses all predictive power when it predicts everything.
Yeah, I mean that's a problem when you have many possible solutions, right? So of course the string theory, sort of quantum gravity, lives at a very high scale, right? And there is no reason why there should be nothing happening between that high scales and the low energy scales that we experimentally access. So it's just, I mean, no one told us that there had to be a sometimes this is called the desert of not having anything between these two very big ranges of scales. Yeah, well, that might be life, and it might be the way. We might have to be cleverer in understanding the consequences of the theory to be able to predict. Perhaps the 4D physics is not completely arbitrary. Maybe there are constraints that should be obeyed, and some maybe coupling constants cannot be arbitrarily weak, so there are conjectures of this kind. But so far, none that is very directly that is both trustworthy and experimentally accessible. But yeah, this is definitely a direction people are trying to look into. So trying to understand general properties of quantum gravity independently of the particular realization for the particular four-dimensional physics, constraints on the four-dimensional physics that would come from quantum gravity.
Well, Juan, thank you so much, for your patience with my beating on the AdS CFT theory and my somewhat naive questions. But this has been such a pleasure. I mentioned beforehand, I've really been looking forward to this for a long time. So thank you so much for taking the time.
Thank you very much. I also enjoyed it a lot, and thanks for all the wonderful questions and the wonderful discussion.
Hold on. If you haven't subscribed, liked, commented, or reviewed, that would be so helpful. And if you haven't yet, you could also follow me on Twitter and Instagram at Robinson Erhardt.